All right, ladies and gentlemen, let's continue and finish this chapter 6 on inertial sensors. And the second topic is now angular rate sensors, gyros, or gyroscopes, as they are also called. And see here an example of a device by Bosch, as they implemented in their system. Yeah, it's an interesting structure that is designed to measure an angular rotation around an axis, this axis here, actually. Yeah. So you imagine where might this be of use? For Bosch, it's part of their, what is it called? The Electronic Stability Program, ESP, or ESP, which implements rotation sensors that detect the rotation of the car as it goes around a bend. And if that rotation corresponds to what the steering wheel says and the speed information says, then everything is okay. If the car rotates faster than what it should, then probably it is sliding, and then there needs to be some corrective action on the brakes to bring it back on track. So this might be one of those sensors, but of course, sensor tech now has lots of sensors, low-cost sensors for the consumer application market, less demanding market. For instance, they developed what they call a Arduino Nicla Sense platform, a platform with an inertial measurement unit with 6 degrees of freedom, plus magnetic field, plus gases and temperature, pressure. It's all in this little PCB, and connectable to a computer, and then with some appropriate software, you can read out all those sensor data. And so, of course, angular rate sensors are also part of that game. So how does that sensor work? Well, you must imagine a sensor that is hinged, anchored here in the center. So there is this center. Let's make this darker. The center connection to which an object is attached that has a shape like this. So this is the object that is being hinged on this fixed center. And these little beams are flexural beams, as we have seen yesterday also in the accelerometer. And those flexural beams allow this mass to move to both directions, oscillate around that center position in at a natural frequency. And this is symbolized by this red arrow that says that it goes back and forth at a frequency omega 0. And of course, if there is no external rotation, well, this thing will just oscillate in the plane of the structure. And now what comes into play is that because of this rotation here, Coriolis forces are in operation, and those mediate now forces, Coriolis forces. This rotation causes Coriolis forces that let this side be moved up and down. Or let me put that in two different colors, up and down, whereas the opposite side moves up and down, where now the colors indicate the phases. So while the right goes down, the left goes up, and while the right goes up, the left goes down. And this is an oscillatory movement around this black axis that goes really through the structure in this direction. And there is this oscillatory motion around that black arrow, that black direction, at the same frequency at which the structure oscillates around the vertical red axis. So without omega in, without this constant rotation around this blue axis, there is no secondary oscillation. And whenever there is this blue rotation, constant rotation around this axis, there is this oscillatory rotation around the black axis in response to the excitation around the red axis. So all you need now is to consider this, this disc-shaped structure as a capacitor plate, and you place some counter electrodes below, on the left and on the right, and then you measure how this disc-shaped structure moves, you know, around the black axis. The left gets closer, farther, closer, farther, closer, farther. Your capacitance on the left is modulated, and then the capacitance on the right is modulated in counterphase, and the difference of those indicate how large that oscillation amplitude is, and the amplitude of that oscillation is proportional to omega in. Without omega in, we have nothing. With omega in, we have something. And again, the structure is fabricated using Bosch's epi-poly process. So we're talking about 10 to 15 micrometer thick silicon grown epitaxially, well, in an epitaxial reactor on a silicon oxide bottom, maybe fixed to the to infrastructure, conductors below, through some holes in the oxide, and then this 10 to 15 micron thick polysilicon, which I could maybe indicate here, with kind of a nominal thickness in perspective, and then it will also see it in the back, but only in perspective. So this plate, this plate structure on oxide on some substrate is released, except where it is really fixed. This anchor point is not under etched, and so here it is really fixed. And for the whole structure to be under etched, actually it is constructed as one of those Fachwerke, you know, I don't know how to say that in English, these constructions of beams with lots of space in between to make the structure robust yet light. And so you see these radial structures, you see pairs of radial structures, and then they're connected by these tangential beams, but in between there is nothing. The silicon was etched away so that the etching solution can penetrate underneath. So at every so if maybe I have to erase a little bit. Oh, that's almost big. So symbolically, the structure now consists of material here, material here. So the silicon is removed in between, and now the etching solution that comes now in here removes the oxide until the oxide is totally removed, and then the structure is released. So this is the idea that we have this sacrificial process ultimately. Now it's yellow. Okay, so that is, and the infrastructure then may contain some electrodes, some subjacent electrodes of whatever construction. We don't see them here now. And then you may also ask, how is this structure excited into oscillation, into this in-plane oscillation? And this is done by extending this disk to the side and then having here interdigitated electrodes. So if I zoom in here, oh, you think that this is solid, but in reality, this structure schematically consists of something like a fixed electrode on this side here. So let's call this an anchor again, connected to some potential, whatever, and then there are these fingers protruding out, These fingers protrude out here, and then fingers of the mobile, the oscillatory rotating structure protrude in between. And of course, they are connected now to the rest of the structure. That goes around the corner here. And that also goes around here, the corner, with other pieces of material. In that background. I hope you see that. So now by applying a voltage between this port here, and so let's call these V0, and then here we have a V, some AC, some AC voltage. You can have an attractive action between these electrodes. This electrode is pulled, not pushed, it is pushed inside whenever there's a voltage difference between these electrodes. The energy of a capacitor, this capacitor wants to be minimized, and it minimizes its energy by making the overlap larger. And therefore, whenever the voltage is different from zero, there is an attractive force. So the frequency of that excitatory voltage will translate into an oscillation frequency at twice the frequency, because positive and negative voltages operate in the same way in these capacitive actuators. The voltage, the electric field direction between the capacitor plate doesn't play a role. It's the same. Capacitors don't know what is front and back or left and right. So, and so by applying these voltages here and then maybe counter voltages here, you're able to also let this structure oscillate. And of course, this is mechanically balanced by having the same mechanical action on the other side. And so we have this oscillation around this corner. And now we would like to know how this out of plane oscillation is generated. And I have, I mean, usually people talk about Coriolis force. You can talk about Coriolis force also in this case, and you may think for yourself after hearing the second part of my lecture, how that could be explained really in terms of Coriolis force. But I'll do it a bit differently. And actually, I identified a video by one of my favorite YouTubers, scientific YouTubers, whose emission is called Veritasium. I don't know if you have ever seen that. He's really good. And so he shows here, let's see. So let's go a bit to the front here. So he's showing this example of an object that swings very fast. This weight at the end of this bar, which is put into high rotation, so it has an angular momentum, and then he lets, he could never lift it up. He tried to lift it up, and then he got this big guy helping him to lift this up at the end of the rod. No chance. But now he's going to show what he can do.
I'm going to let go with my left hand. What you'll see is that the shaft remains horizontal. You can see it going around there.
It almost looks as though the wheel is weightless. How does this work? Well, instead of pulling the wheel down to the ground as you'd expect, the weight of the wheel creates a torque which pushes it around in a circle. You may recognize this as gyroscopic precession. For a more detailed explanation, click the annotation or the link in the description to see my video on the topic. Here, I want to try something more
And it felt incredibly odd.
Yeah.
So what I want to say is that actually you can interpret this motion of this gyro in terms of this precession physics also. And so let me explain how this goes. Let me close the bracket here. So we're talking about angular momentum, and moments of force or torque in this area. And so you can imagine this rotating, this oscillating mass to be like a top. Yeah. How does one say a top in German? Ein Kreisel. Yeah. Kreisel. When rotated and stands on its tip, and tip over, and then it starts to process a little bit, and while it's going down, or the top down, some point it falls over. That's why I drew it like these tops. Yeah, I think this is called a top in English. Yeah, yeah, and so a top rotating has, of course, an angular momentum. Mass that rotates has an angular momentum. That's one of the conserved properties in this world, and this angular momentum is a vector. Yeah, it goes in the direction of the rotation. Yeah, usually the sign is that the rotation direction is indicated by a vector. Yeah, so that the rotation is like the right hand. The thumb goes in the direction of the arrow, and then it rotates around this. So this is the only hand rule that I remember, because I may have told that, left hand, right, left foot, right foot. I never know. Yeah. So, but this one somehow I see it because I see my finger curve around. Yeah. And I'm a right-hander, so it's easy for me. Yeah? And so this angular momentum, yeah, this vector is indicated in bold here, like the moment of force is also indicated in bold. And moments of force have the ability to change the angular momentum. It's clear if you have an object that to which you apply a moment of force, a torque, it starts to rotate, and if you apply more of that torque, it starts to rotate more and more, so its angular momentum changes. Yeah, and the relationship between momentum and angular momentum and torque is that the time derivative of the angular momentum is equal to the torque. So that's what I call JMR. Yeah, the angular momentum moment of force relationship. I have abbreviated it here also. And so now what happens is that in fact we have an excitatory moment of force that lets this top spin once in positive, then in negative direction, positive, negative. So that torque causes that change of angular momentum around this vertical axis, and therefore as m becomes positive, negative, this mz, yeah, there is a rotational rotational angular rotation, yeah, on the right, left, and so on. But this top now, under the influence of an external rotation, of the system of coordinate to which it is attached at the bottom, that system of coordinate, that z now moves to the back, no, to the front, under the action of that external rotation speed. Yeah, so as a consequence, there will be some moment experienced in that third direction, and we want to understand why. So if I just write down the JMR in the two components which are important here, namely in the z direction and in the x direction, this vector j is equal to a component in x direction times the unit vector ex plus the z component in the unit times the unit vector in the z direction, and then the time derivative is of course the time derivative of these components. And this is equal to the moment in x direction times ex plus the moment in z direction times ez. So this is the basic equation that we just saw up there just now, separated into the two relevant coordinates. And then there is another point that is interesting to observe, namely that I made a little transform. I replaced this Jx by this object here. And so how did I do that? Well, when you have a vector like this vertical component of J, so now the J is in the original Z direction, but now I'm rotating it around this y-axis. Of course, I mean, if I just took this vector and rotated it around with the angular velocity omega in, the vector would of course describe this circular trajectory, and so the time derivative of J is actually a vector that points towards us. Time derivative of this vector of constant J, if it is just rotated as a solid body, is a vector that comes toward us, and that's what is meant here, that the vector Jz is now rotated with this coordinate system in this direction, and therefore the J component, the change of the X component, it grows, just like that. The speed of rotation, the rate of change of Jx at this initial moment is given by something proportional to the length of J, and then proportional to omega. That's a classical connection of physics, that is applied in many cases. Any vector being rotated as a tangential component, and that tangential component is given by this kind of rule. So what we see is that if we have Jz, now if we have Mz, we probably can calculate Jz, and if we have Jz, then we can also calculate this component, and then we also know Mx. So that's kind of the logic steps that we go through. So we will set Mz as an oscillatory moment of force with an amplitude or magnitude M0, and then this e to the I omega t factor. It says that it oscillates, the moment, the excitatory moment here oscillates with angular frequency omega, and then the Z component of J is then in the simple model easily seen to be M0 over I omega, because Jz dot is of course equal to I omega Jz, because the time derivative just lets I omega come down, and then rearranging terms, we have this value of Jz of t, which is proportional to M0, of course, and oscillates with the same frequency, and then it depends on the frequency. The larger the frequency in the simple model, the lower the angular momentum and magnitude will be, because there is no time to build up momentum under the torque. And then in a simple model again, if we then just implement Jz in here, we immediately have that Mx is proportional to M0 and proportional to omega in, and it depends also on frequency, but it oscillates also at the same frequency as the excitation moment of force. So that is what this means, and physically it would mean that if you held that bar in your hands here and here, and you were and then there is this top being wiggled back and forth, and you're trying to rotate it, you're experiencing a moment, in your direction, because the Mx points towards you. And of course, the flat top, Bosch's flat top, experience the same. It is held by these little arms, and it rotates around those little arms and executes that oscillatory motion, and that can be measured. So that is what happens. And now, if we want to model that a little bit more sophisticatedly, then well, we can think of the fact that if a mass and a spring is an ideal oscillator that has a natural frequency, then probably a bending beam, a torsional spring, and a torsionally mobile mass will also have a natural frequency, but it could also be damped by some phenomena, by some squeeze film damping. But we need to model that. So how is that modeled? It's modeled by an equation that mimics, or that is the analogy of the linear mass motion under a spring constant and a damper in the following way. First of all, the degree of freedom is now not the position, it is the angular position. So it's the deflection from some original or some initial angular position. So here the angle increases and then it becomes negative. So that's how this theta is defined. And a body of a mass distribution has then an inertial property with respect to angular motion, angular acceleration, that is called the moment of inertia, theta. That is obtained by the integration of the mass elements multiplied by their distance from the center of rotation, and then you calculate that and you see that the moment of inertia increases, like, I don't know, the fourth power of the size or something, or a second power of the size, quadratically, because elements more at the center don't play so much a role, and then those farther out, of course, play a larger role because they're accelerated much more under an angular acceleration. So this is the angular rotation. So this mimics basically this term. And then, of course, we have a spring constant. This is a rotational spring constant. I have symbolized that here, or reproduced this graphic where k theta is symbolized by some spring acting over a length from the rotation center. This will drive the system back to angle theta 0, and it costs energy to deflect it from that angle theta 0 proportionally to this deflection. And so this is well modeled by this k theta, symbolizing the kx. And then we also have the damper, which here could be symbolized by some damping element, also attached as a distance, at a distance from the center of rotation. So this mimics the dx dot, the velocity term of the damped harmonic oscillator equation. And then this is usually equal to the force that is applied to this oscillator, the force of T. And here now, instead of the force, we have the rotational force, which is called torque. And so if I now try to solve this equation for a given excitation, what will be the angle be? Well, I can predict immediately by analogy that if I apply an oscillatory excitation, an oscillatory torque, then there will be an oscillation of my mass with a magnitude that probably depends on frequency, that undergoes a resonance curve, like X underwent a resonance curve in response to an oscillatory excitation in the linear case. And so there will be a natural oscillation frequency. There will be a Q factor that I can take over 1 to 1 from the linear case. The natural resonance frequency is kappa theta over the moment of inertia, and then the Q factor is omega 0 times this moment of inertia divided by the damping constant, and so those quantities can be calculated if you know the geometry of the structure. The geometry goes directly into this thing, and then damping constant, the geometry and the squeeze film damping will certainly reflect that. And the spring constant is now the spring constant, the bending stiffness of that flexural spring that holds everything in place. So if I apply now this boundary condition or this driving term on the right hand side, I can immediately write down the solution from the linear case, can take it over, and then we have a magnitude that depends on m0 over theta divided by square root of the usual form, where we have a natural frequency and then the Q factor implemented in the same way. So this is a resonance curve that we expect, and there will be a phase shift also for that phase shift for that angular frequency, which is equal to arctan, and the bracket somehow moved, all the way. So this should be somewhere here, exactly like in the linear form. And so that is the motional solution for this excitation, and then we can calculate the angular momentum. The angular momentum is equal to rotational speed times rotational mass. Mass times speed is momentum, and here it's just for the angular part. Theta takes over the role of the mass, and this is the speed. And so we can calculate the amplitude of J and its phase shift, which adds another factor, another term pi over half because of this derivative. And so that's how we model the original excitation. And now of course there is this second component now for rotation about the x-axis. Now there will be, of course, some theta. What do I write? This whole system, due to its geometry, will have a moment of inertia theta around for rotation around the x-axis. It will have a damping coefficient theta for rotation around the x-axis, and it will have a spring constant theta for rotation around the x-axis. Actually, I could simplify that theta by saying, okay, there is an angular rotation, theta x. So that would be, if I go back to here, if I say that this vertical position is so the angular rotation around this axis is manifest by a reference position, which is here in the center, and now we're rotating around that axis by what I call theta x. Whereas this rotation around here is called theta in the graph on the next page. So it is. I know it's unfortunate that the axes are now rotated here. What we look at here is from the top. On the top, this is viewed from the top, and then in perspective we now see the theta x apparently in the same direction as here. But it's of course 190 degrees. It's hard to imagine. It's in this vertical plane, in perspective, let's say, it gets worse and worse. So stop. No more improvisation. So this angular coordinate theta x, that describes the rotation around the x-axis, can then be used. And of course, I mean, this mass now has parameters that lets it have a natural resonance frequency around the x-axis. And it also lets it have a Q factor around the x-axis, for motion around the x-axis. Whereas up here, actually, we had a q which properly would have been called qz, as the omega 0 properly would have been called omega 0z. No? And so this is all built into one big formula. So once we have jz, we can compute mx. And once we have mx, we can insert that mx in an equation, like this, with mx standing here, and then theta x and all the x parameters, describing the motion of that system. And then that can be solved, and then we obtain a theta x of t is equal to the original excitation around the z-axis multiplied by frequency multiplied by omega in, proportional to omega in. How does one write proportional? Like this. At the same frequency as the excitation frequency. And then we have a frequency dependence at the bottom that symbolizes both the frequency dependence of the original oscillation, the real oscillation that then produces an angular momentum that is moved by the external angular rotation, which then translates via another oscillating system into the out of plane motion. So that's why we have these two parts here. So basically solving for mx and theta x produces this solution, and what goes in already has an omega dependence because jz depends on frequency because it is the result of an oscillation, and also rotation oscillator. So this is a complicated curve, and when you plot it, for some systems, for instance, for a system which has the same Q factor for both in plane as out of plane oscillations, it has the same resonance frequency for both modes. Then, if you're lucky enough to have designed it right and the technologists produced it right, and there was no error and no minute deviations from the specs, then you will have a curve that is peaks sharply because it is kind of the square of a resonance curve. It really peaks out, highly sensitive. But then also you need to hit the natural resonance, the common natural frequency omega 0, which is then omega x equals omega z, really fine. If you're beside it, you also have a curve that drops very fast, and then you will have a lower response. And then if you don't know that you're beside, you think that the angular rotation is actually weak, whereas if you were on the top of the curve, you would see that maybe it is much weaker than you think, because then you would have it really amplified. And so it is not necessarily a good thing to design the structure to have the same resonance frequency. By having parameters that are slightly different, you can make this peak a bit flat. And then your driving frequency can be within a range, with an inaccuracy, or the system might drift a bit and you don't feel it. So for a stabler operation, it may be better not to have the resonance frequencies at the same. Of course, the sensitivity then goes down. This curve reaches a maximum at 60, whereas here it reached a maximum at 100, which is probably Q was 10 here. So I think that Q equals QX equals QZ. That probably was 10. And now with this improper matching, we come down in overall sensitivity, but the good thing is that you're less sensitive to mismatches of the frequencies. And if you take those excitation frequency and the measurement natural frequency apart, then you have this secondary minimum, or this minimum in between, and then well, you can be quite inaccurate with your frequency, and Yeah, so maybe low cost sensors, low performance sensors can be operated. But I mean, you know, the design details of these sensors is something which, of course, is every company's own, the result of every company's own thinking. Yeah. Yeah. So now here is the second example of a structure that is also used by Bosch. Yeah. The tuning fork gyro. Yeah. And here actually I can't do or it's easy to interpret everything in terms of Coriolis force. Yeah. So I have been showing the Coriolis force down here. Yeah. What is it? Yeah. So let me show the Coriolis force again in an animation from Wikipedia here. Can I make this bigger? Yeah. So what do we see here? Okay, we see a plate, or is it? This rotating plate that rotates around the center point. Yeah. And then a ball rolls or glides down without friction from top to bottom. Yeah. And so that's you know, that's what we would have if this plate was fixed, and then I would give this ball a little impulse, and then it rolls towards me. Yeah? That is my reference coordinate system. Yeah? And that's what the ball is going to do anyway. Yeah? Even if the subjacent plate rotates, the ball has its inertia, it comes towards me. Yeah? However, from the point of view of an observer, that is symbolized by this dot on the plate. No, the ball, while the ball rolls towards the bottom, the red point goes to the right. Yeah, so this observer sees the ball first coming to him, and then it is deviated on the side. And this is symbolized by this this curved trajectory. Yeah? So it looks like for the person who is on the disk and who doesn't know that the disk is rotating. It looks like this ball experiences a force. There's an apparent force. It's apparent because the observer doesn't know it's his fault because he's rotating. It's not a physical force, it's an apparent force, but it is useful to describe what happens in the reference coordinate system of the rotating observer. If we didn't know the Earth was rotating, we couldn't make sense out of those weather systems where negative pressure zones attract air and then start to rotate, counterclockwise. What forces are in operation there? It's impossible. Air masses should contract until the pressure is the same. No, they don't just contract, they start rotating. And expanding air masses expand, they don't just expand, they rotate in the counter motion. And when you go to the south, it's just the opposite. So what mysterious forces are in operation? Well, to model that in the reference system of our human-centered world that doesn't move, where we observe these strange phenomena, we will introduce the Coriolis force to explain or to model those strange notions. And those apparent forces are easy to write down in terms of, you can do some kinematics analysis, and then you will find that the correct force, modeling, or giving a correct model of this apparent behavior is given by 2 times the mass of the object moving here at a speed v in this rotating coordinate system, with rotating at an angular rate omega. Okay, so this is how you model it. It's the cross product of the velocity cross the angular rotation vector. So these are vectors, of course. Now, so when we look at this this tuning fork, what is this tuning fork? A tuning fork is an object with two arms that swing asynchronously, or synchronously, but in counter motion. And that has the advantage of generating no moment of no angular, no torque, no moment of force down here at the base, because the two moments of mass times acceleration, force times L corresponds to some torque acting on this base, but it is counteracted by this one. So those basically just compensate, and that's why a tuning fork can resonate for a long time, because there is no energy loss into the base. If you only had one arm, and let it swing, it will come down very fast. There would be no chance of hearing this one arm sound in your ear by the time you reach your ear. But with two, it's okay. It's kind of a closed resonant system. And so these arms are excited into resonance in this direction, that direction, and then of course in the other phase in the opposite direction, back and forth at the natural frequency, again determined by some stiffness of the material and some mass density that needs to be moved. And now this whole system is rotated around this this axis, with this omega vector, angular rate vector. Okay, so it will, the left comes towards us and the right goes away from us. And now, if we are now sitting with that coordinate system, with that tuning fork, and we are rotating at the same time without knowing, because the Earth rotates so low that we can't feel that, we don't get dizzy, then we will observe interesting phenomena, namely that although we excite the tuning fork sideways, it will also swing out of the plane. So the right arm will come towards us and then back and towards us back, while it does the left, right. And the two arms are going to swing opposite. And that's because obviously we are in a rotating coordinate system. If that tuning fork is still, it will just do what it does. But as soon as we rotate, it will have this secondary motion also. And that secondary motion is the effect of that Coriolis force. I can do now, let's say the yellow arrow V, V cross, so V cross omega, V cross omega makes an arrow that goes into this direction. Please correct me if I'm wrong. I'm the hero of wrong signs. So V is like X cross Y is Z. I think it's okay. Today's prediction is correct, or I think, until somebody disproves me. So while this arm here, V cross omega makes an arrow that goes in the back. And then when the arms swing back the green way, then we will have the opposite response arrows. I see. Acrobatic motions to understand what happens here. So how do I do cross products? I always do cross products by X, Y, Z. X, Y, X cross Y makes Z. And then the rest is only reorientation of that thing. That's sometimes the challenging thing. Twisting the head internally until it sees the X in the right direction. But it's always what is the first times the second must give the third. So in which direction has the third axis to look like? Okay, and so this is how this operates. Yeah, and if you had now a sensor that were able to detect that out of plane motion of those two arms, for instance, using a piezoresistive transducer integrated on those sides, measuring the bending, the compression and expansion of this arm on the front or on the back or everywhere at the same time, you could use those signals to determine this out of plane motion, and you would have a musical tuning fork able to at the same time measure the rotation of the how do you say, dirigent, the conductor, yeah, on his podest. Yeah. Okay, and so this is the idea that is implemented in Bosch's tuning fork gyro, and there are many examples from other companies as well. This is again done with epi-poly technology. Let me magnify this a little bit so that we see it. We have seismic masses here. So these are the two tuning fork arms. Yeah, they are excited back and forth into this back and forth motion. How is that done? They're attached to this lever arm, and that lever arm is attached to some electrodes, and those electrodes are fixed in their position with those very gentle flexural springs that allow them to move only in that direction. And by construction, this doesn't rotate. Yeah, it just moves uniaxially back and forth. Whatever is occurring in the back, if this goes sideways or front or sideways, yeah, this just moves in this longitudinal direction. And here you have the counter electrodes. So you can imagine that this is again V0, and this is some V or V drive. And you can excite this this mass into motion back and front, back and forth. And then this mass is this other mass is also excited, and so they move in counter in out of phase, perfectly out of phase, in counter phase. And then attached to those masses is a more complicated detecting structure. So this framework of beams is attached to this mass and then to that mass, and now under a rotation around a vertical axis with some angular rotation vector omega in, because of the Coriolis force, again, V cross omega in makes yes, the solid blue times the out of plane blue makes the solid red, and in the back motion, opposite. And here, this solid blue times solid red makes the and this out of plane blue makes this solid red here. Next, duck. Yeah, it's correct. So what will occur is exactly what occurs with the tuning fork. Those masses move in the red direction, also in out of phase. Which means that you can now attach a framework here, and this shift in one direction and retraction in the other direction will cause some rotation, and that rotation is sensed back here. So that is basically how the structure works. This structure is rotated, and then some electrodes are increased and others are decreased, or some capacitors are increased and others are decreased. And so this detection of that rotation of the structure is measured down here. Yeah, and of course the design of the resonance frequencies and of the damping coefficients and so on, that's Bosch's know-how. Here you have an example of an inertial measurement unit, an earlier version, today's version now. are quite small, but here you have a gyro, you have an accelerometer, you have an ASIC hybridly integrated with those micromechanical parts for economical reasons, because although one could integrate MEMS with circuitry, as we know, we have seen these ways of CMOS integration. In this particular case, Bosch says, well, if we want to change our circuitry, we can use the old gyro, the old accelerometer, and then put there the more performing circuitry. Or if we want to replace the gyro by another version, then we can also do that if it fits the circuitry. So the modular aspect is of course given. You don't have to redevelop the whole system from scratch and get everything working again as a whole. We can concentrate on parts, and that in a development path is often a more economical way. And then finally, I would like to show you another idea that is also around and still inspires people up to now in the papers. It's an old idea, but as I say, you find it still today. It's a so-called vibrating ring gyro. And the vibrating ring gyro has much to do with the so-called wine glass gyros. A wine glass gyro. The wine glass gyro is actually the gyros that, for instance, Litef produces for the high-end applications, for the plane navigation applications, where you have angular rotations of a few degrees per hour. That's not a lot of angular rotation. Yet you need to measure that to know where your plane is. And independently of any satellite communication, it could break down any time if somebody shoots up some disturbing electromagnetic pulse or shoots down some satellites. There are such crazy guys. And so these mechanical gyros ensure that planes can arrive independent of such information. And the wine glass gyro, and those are really made from a ball structure of glass, that has also been reduced to micro size by, again, Najafi and others from University of Michigan, to micro size with micro glass blowing techniques, very, very subtle developments. And the fact is that a wine glass has resonant modes, of course, as you know. You put your finger on the wine glass and you get it to sound. You excite it into a vibrating motion that has likely in the ground mode, in the fundamental mode, a shape like this. Contraction on one side and then expansion perpendicular and then periodically. So this is kind of a wine glass, and then in those early days, people said, okay, let's make the planar wine glass. We can't fill it, but it resonates like a wine glass. Let's make this structure like a beam structure, circular beam structure, suspended in the center, so that it can expand and contract like this. And this is done by technology that is pointed out here with some substrate and then some sacrificial layer and then some photoresist electroplating and then some electroplating, in this case of, I think it was nickel, and this nickel structure that you see here now from the side, it's suspended in the center. And when you look at it from the top, you see here the center, 4 curved beams that can bend, and then this outer ring that can bend also. And so now to excite this structure, what you need is lateral electrodes. So you can imagine that you add some electrodes here, and this, and here. Hmm. So this would already be enough. So you again apply V0 here and then some V in or V drive out here. Yeah, we apply an AC voltage. And that AC voltage let the central ring expand and then you release it and you expand it again and you drive it into resonance. Yeah. And now comes the external rotation, which is an omega in around an axis that points towards you. So the rotation is indicated by the circular arrow here, and of course the vector stares right at you. And so under this effect, the resonance mode of this gyro in your frame of reference, as you rotate with the gyro, you see the gyro all in the same position, will cause some motion where the originating oscillation that is aligned with the exciting electrodes somehow gets shifted. There's an off-axis component of that oscillation. So the maximum bulging out of this circular object, the maximum amplitude is here, and then the nodes, instead of being here at 45 degrees, are now also shifted to other positions, and that angle theta is proportional to the angular rate to which the sensor is exposed to. And so now, how does one understand that? I think you can also understand it in terms of Coriolis force, because you have a velocity vector v, you have an omega in out of plane, so v cross omega must be a vector f Coriolis in this direction. V cross omega, yes, I think that's correct. And so there is an additional force acting on this mass now in this moment in this direction, and here in this direction, and here, let me think, in this direction, and here in this direction. So the same beam masses are not only excited into this radial direction, but also in tangential direction. And that tangential motion causes this object to respond with a distortion that, of course, has its maximum around 45 degrees. And the superposition of the initial excitation and this secondary response causes a distortion whose maximum amplitude shifts linearly with theta in. So that's basically an addition of two components, like a sine with a cosine, with a prefactor that can grow, causes the sine to be shifted slightly, in position. That's exactly what happens here. And so these gyros have been miniaturized a lot, and actually I think I should dig out some modern slides about that from the Najafi group, to show how this is done with this microglass blowing techniques, and then how electrodes are also attached close to those glass structures, and what it implies in terms of resonance frequencies and sensitivities. But these micro gyros are quite highly performing now. And I think this is the last slide of my lecture. What time is it? Don't even have a watch here. Yes, I have. So this concludes my lecture here. If you want, I give you some information about the exam also. Several of you have registered for the exam. I think not you. but you did. Yeah, you did, yes. So so those who have never spent an exam in my with me, an oral exam, it will be an oral exam. We will be sitting at the same table, like I will be sitting on that side. I can actually stop. Well, maybe it's interesting for those who are not here. If somebody, yes, I'll continue. Yeah, so I'll make a sketch. Yeah. So here is my office. These are the windows. Yeah. Here is this table. Yeah, here is my office table with my chair. And then that's the end of my office. There's a door. Yeah, there's another door. So that you can represent that. Yeah, and yeah, you will be sitting here. Yeah, I will be sitting here. OP, and then there is a third person, the observer or the guy who takes the minutes, who notes the questions that I ask you to make sure that it is documented and I'm fair with you. Yeah, which I definitely intend to be. Yeah. That's the first premise of a professor in an exam. Yeah. So, and then you will you may see some poster here with actually some structures. Yeah. So it could be that I will ask you, do you reckon does this structure, stimulate something in your head? Yeah, and then we have a starting point. Yeah, but before we are there, I will ask you to summarize the lecture in a few sentences. Yeah, I wanna see if you got the structure of the lecture right. If you can spell out the chapters and the main subsections of the chapters. Yeah, that are there. Yeah, this is something which you can learn very well. Yeah, I mean, it's part of your learning process anyway to know what is where in detail, but to have it in the rough way allows you to come into the exam kind of relaxed because the first chapter was about some this, and then we had this technology chapter with different methods, and then we had this magnetic chapter, and we had this stress sensor chapter, and we had thermal chapters, and within each chapter you mentioned maybe the 2 or 3 subsections that we had there. Yeah, the types of devices, thermal devices. Yeah, we had the radiation sensors, we had the pressure sensors, and we had the thermal converters, and that's it. Yeah, so that you can feel at ease, and then I will usually ask you, is there something which interested you more than the rest? And then we can start talking about that topic. Yeah. And then if you say, oh yeah, I really like the micropyramid. Oh yes, I always wanted to talk about resonance frequencies. Yeah. Okay, then we'll talk about that. Yeah. And then we'll talk about other things as well, because I mean, it's easy to jump from one thing to another, in a more or less orderly way. Naturally coming from one topic, and we say, yeah, but there you said, this isn't that related to this other topic as well? Could we have a look at that? And so what I expect of you is that you can talk about what we talked about here, that you can make sketches about what we sketched here, that you can write down essential formulas that we talked about here, that you can explain what those formulas mean, and that you can tell about the assumptions that we made to simplify things, that you can mention some quantitative things, how far can one under etch with Swift etching, how long does it take, practical things that are also good to know. Yeah. So this is basically how it goes, and so it's going to be a discussion back and forth. I'll ask something, you ask something. I will be stimulated into some new question. You will be stimulated into some new answers, and so it's a conversation between educated people. That's how I like to see it. Yeah, and while doing so, you scribble many things on the paper in front of you. You have some pens. You can take your own pens if you want. If you have some pens that stimulate your thought better than others, take your own. I have some. Thinking and writing is very strongly connected. In my head. And so this is it. And after 25 minutes, before you even notice that 25 minutes have already elapsed, I will tell you, or the Beisitzer, the observer, will tell us that we have 5 more minutes, and then, or after 20 minutes, he will tell me that there are 5 more minutes, and then I should think of closing. And then after 25 minutes, it'll be over, and then I will send you out front of the door. I'll talk briefly with my collaborator to see your result in the light of other results, and then give you a grade that fits. And then I'll call you in again, and we can talk briefly about how you felt and what conclusions you draw, from your experience, and maybe some recommendations that I can give you, and of course, the quantitative result of everything. So that's how it's going to happen. And it's going to happen in building 103. 103 in the ground floor, EG. Where you walk into the building, you take the long gangway, and I'm the last office on the right. There's also a toilet just opposite. It's a unisex toilet, so everyone is allowed to go there now. So, yeah, and very nice. You have a beautiful view of the Black Forest here. So the sun is shining, everything is beautiful, and at the end you have an exam accomplished. Are there any questions? You can bring your notes, of course, but you leave them in the bag. Yeah. Yes. Yes, Anya. Of course you can. Of course. Well, German or English, please. Not Chinese. Not Chinese, not Indian. One of the many Indian languages will be tough. Or Pakistani, I don't know. Yes. To what? Well, I evaluated, I rated all this already. I made my sums and so on. So you all passed. Yeah. That's okay. You don't need to bring those because you will not do calculations. I will not ask you to solve a problem. I'll rather talk about your understanding of the things. Thank you. Yeah. Yeah. Any other questions? Okay. Don't be shy. Okay. Well, then we can close this. And I thank you for your attention over all this hot semester, coming here physically. And I wish you the best for the continuation.